So today I will go through the sections that we have discussed in the last session. After that, I will proceed with the new topic that we are going to discuss today. So in the last class, we discussed on adaptive filters and especially about how we can find the optimal filter coefficients for that kind of adaptive filter. So an adaptive filter is a filter which updates its coefficients based on the error that can be observed with the output of the filter and the desired signal. So based on the error value, the filter coefficients get updated with the time. So we require this kind of a updating filter for cases where the signal that we are inputting into the filter gets changed with the time. So for cases where the input signal is a WSS signal or a stationary signal, the filter coefficients actually remain the same. Once you find the optimal filter coefficients, that would be enough for all the time instances. The reason being the input signals statistics don't change with the time. In cases where you have these non-WSS signals, then of course the statistics of the input signal to the filter changes with the time. In that case, we have to consider that also into account, and we have to calculate the error, and then based on the error we have to calculate the optimal filter coefficients for that certain time period, and then we have to update the filter coefficients of the filter, and we have to make our output as close as much as possible to the desired signal. So when we consider about the non-WSS signals or non-stationary signals, then we derived like metrics to denote the input autocorrelation of the input signal. So this signal considers a finite length of the input signal, and the finite length consists of about m number of samples, and we form this matrix. Next, we create another vector, which is Rxd. So this vector is known as the cross correlation vector, which is the cross correlation between the input signal X and the desired signal D. So we can form the expectation of the cross correlation using this expectation between Xn and Dn. So also for this cross correlation vector, we can consider up to m samples by considering m samples of the input signal and comparing it with the desired signals samples. So when we are going to update the filter coefficients, we have to find the filter coefficients for a certain m number of finite samples, and the optimal filter coefficients can be found using these Wiener-Hopf equations. So Wiener-Hopf equations can be calculated. The optimal filter coefficients can be calculated by taking the inverse of the input correlation matrix and the cross correlation vector. So actually finding this answer to this equation is computationally costly in most cases. If you consider taking the inverse of a matrix, it is computationally costly, and it keeps increasing if the number of data samples we are considering for a certain time is large. The m value, if the m value is quite large, then the R matrix is also going to be large. And if that is the case, the computational cost of the operation that we are doing here when taking the inverse, and when we taking the product between the matrices is high. So in such cases, this problem, and then also we also have another problem where we don't know the statistics of the input signal. For example, statistics means we don't know the probability density function of that input signal. So in some real world signals, we don't know the exact probability density function. So therefore we cannot like derive statistics of the input signal properly, and therefore we don't have that information as well. So in such cases, we will be going forward to like practically possible methods. So the solution is using algorithms such as steepest descent algorithm or else least mean square algorithm. So steepest descent algorithm is one solution, and in that method we can solve the problem of complexity. But in there actually we have to have the knowledge of the statistics of the signals of the system. For the least squares method, we can solve both the problems, solve the complexity problem, and solve the equation without knowing the statistics of the input signals. So therefore, we can go ahead with least mean square algorithm for almost all the cases. For the steepest descent algorithm, we decided like how we can determine the learning rate mu value such that we have some filter coefficients that will converge to a certain value after multiple iterations. So if we choose like this is the equation that we use to update the filter coefficients, and we are trying to get converged filter coefficients after some time. So so in order for us to get an converged value, we need to decide the range of mu, and we derived how we can find the optimal mu value for the step size of the this gradient descent method. So yeah, step by step increasing the value, increasing or decreasing the value of the coefficients. So that step size is given by the mu. So the mu value has to be between a certain range, between certain bounds. So that we calculated and we decided using this derivation, and we were able to determine that mu value should be between um, like 0 and the 2 over lambda max. So in lambda, what we mean is the eigenvalues of the correlation matrix R, or the main correlation matrix, autocorrelation matrix. We are considering this equations where this auto Rx is the matrix we are considering as the autocorrelation matrix of the input signal. So the eigenvalues of that Rx signal can be calculated. We can take the maximum eigenvalue, and then we can take that value in here. So we can determine this that the step size should be between these two limits, and if it is that, then we can find like a convergence in our field coefficients, right? So our field coefficients will converge after some time once we do the updates of filter coefficients iteratively over time. So this is how the error of the filter output will change over the time. So firstly, once we have certain filter coefficients initially, the error of the filter output and the desired signals values, the error between the desired and the filter output will be high once we have a filter coefficients that are not optimal. So once we update over the time the filter coefficients, they will converge to a certain value, and then that will reduce the error of the filter output as much as possible, and that minimum error value will be reached. For the LMS algorithm also, we have an update equation like this. This is the one for the LMS algorithm. In there, actually, we consider the mu value here as well, and the impact of xn and the error signal. So in there also, we are taking the output, and we are taking the difference between the desired signal and the output signal of the filter. The only difference in here is that we are actually measuring the error signal value, and based on the error value, we are updating the filter coefficients. So the similar analysis can be done to this filter coefficient update equation, and we can find that the step size for the LMS algorithm is also between 0 and 2 over lambda max. So LMS algorithm is a simpler version of the stochastic gradient descent algorithm, where the stochastic gradient descent algorithm is considering, it is considering stochastic data samples each time to calculate the gradient at each time, and then based on the gradient value that is observed, it decides like what is the step size and how much of increment needs to be done on the filter coefficients and so on. So the stochastic gradient descent algorithm is a like a bigger algorithm, and it is to be like studied extensively, but currently we have discussed one primary example of stochastic gradient descent algorithm. So this primary LMS algorithm is the most simplest one, and that can be used for the moment for our prediction purposes. After that, we started about stochastic models that we can use for time series analysis and time series prediction. So that is also something related to what we discussed in the previous sections and about adaptive filters and so on. So in here, what we are trying to do is that we are trying to predict the time signal of a certain process, and we are trying to predict the next signal components or the next future behavior of the time signal. So if we have the time signal up to a certain point, we are hoping to predict the next points of the time signal. So in this time series analysis, the objective is to predict and forecast the time signals. So we are using the known data values, and we are trying to fit those data values to a certain time series with suitable model parameters, and we are going to estimate the next values of the signal using those parameters. So we have to know the nature of the time series, and then we can predict the future. So we can use many kind of stochastic models to model these kind of time series analysis, time series signals. So the time series signals that we are considering are like random signals with random behaviors. That is why we are going to consider stochastic models to model this time signal. So you can use stochastic models to model this time signal. So when we consider the different models that are available, there are many models. So one such model is the ARMA model. The ARMA model is a model which is known as autoregressive and moving average model. So that this model is a model that combines the effects of two other models, autoregressive model and the moving average models. So first we discussed about the autoregressive model, and the autoregressive model is actually I first used the concept of random processes to explain about the autoregressive model. So actually autoregressive model is used to model the time series signal, right? So certain time series signal, and that time series signal is a combination, linear combination of multiple um, time variables. T1, T2, T3, T4, T5. Those are actually random variables. So we are considering something similar to the random processes that we discussed, I think, in the very beginning of the lecture series. So the time values that we can consider in here, time, T1, T2, T3, T4, likewise up to Tn, they are all random variables. So the values that we have for each time instances of the signal can be combined together, and we can form uh, a linear combination of all those time signals, and we can make it equal to uh, to a certain xt value, or to a certain amplitude at a certain time instance of the time signal. So this linear combination is actually a combination of random variables, xt minus 1, xt minus 2, xt minus 3, xt minus p. All those variables are actually random variables, right? And so this equation that is given in here is basically a equation which shows a combination of random signals equaling a certain current random signal. So once we actually, so this equation gives us the relationship between the past values of the time signal. Xt minus 1 is a past value of the time signal. Xt minus 2 is another past value of the time signal. Likewise, up to p past values of the time signal are used to model the current time signal value, xt. So the current like random variable which is related to the time t. So if we know this equation pretty well, which means that if we know that the parameters phi1, phi2, phi3 up to phi p, we can use that knowledge to like predict the current output at xt. So therefore we can actually do a lot of things with that. Therefore we can use that to do future predictions of time uh, time values, like time signal values. We can predict the signal value that is occurring in the next time instance. So if we know a relationship between past values and the current value, then we can predict the current value using the past values. So the challenge is to find this phi 1, phi 2, phi 3, that kind of parameters. That is one thing. And then another challenge is to, um, like if we are going to use filter and all, we also have to find filter coefficients uh, as well. So we will discuss when we come to that point. So the challenge is to find the parameters that are defined basically in this equation, like phi 1, phi 2, phi 3, phi p, likewise. The challenge is to find the unknown parameters. After that, so we have another thing, which is the another model, which is known as moving average model. So this is the equation for the moving average models. So in order to reduce the limitations of the moving previous model, the AR model, autoregressive model. So we have actually, in the AR model, we have not taken into consideration the effect of correlated noise or unobservable noise, which is available in the time series. So in order to take into effect of all the unobservable noise and the correlated noise, we can consider this moving average model, which takes into account all the noise samples which affect the current signal. And these noise samples can also go up to past values of q past values. And so all the combination of all the past values of this noise values are taken into consideration when defining the current value of the signal, signal xt. So the xt can be modeled using past values of the noise. Apart from that, we can then combine the effect of both the models, and we can form the ARMA model, which is defined as the combination of the past values of the input signal, like past values of the time signal that we are considering, and the past values of the noise components that are getting added. So all these components will determine the current value of the time signal xt, and then it will also be affected by the current noise that is added to the signal. So this is the model that is finally used to model the process using ARMA model. So this equation that we have here has both the combination of the AR processes and also MA models, AR models and MA models. So that this is known as ARMA model. So sometimes we have some problems with the ARMA model. So ARMA model is basically used to predict predict random processes which are stationary. So the random process that we take as xt, right? Xt is a random process that we use to denote like a general random process that is governed by the random variables at t1, t2, t3, t4 up to tn. So the time is the variable, and we use xt to denote a random process that is determined by the different time instances and time variables. So the xt value or the xt random process will uh, will sometimes be stationary or non-stationary. If it is stationary only, we can use the ARMA models. However, if we want to use it for non-stationary processes, non-stationary xt processes, then we have to consider using ARIMA model, which is known as autoregressive integrated moving average model. So ARIMA model is an improved version of the ARMA model, and that model is able to predict signals and model signals which are non-stationary processes. So ARMIA model means autoregressive and integrated moving average model. So this is a more improved version of ARMI model, if you can understand, because it can model non-stationary signals also. So in real world, we normally we have a lot of non-stationary signals, which are very random, and we don't know their probability density functions, and therefore we cannot really predict its output that will occur in the future. So in such kind of cases where we don't know the process properly and we cannot model it using a stationary process, then we have to consider that as a non-stationary process. And if it is non-stationary, it has to consider different aspects of the signal behavior and its nature. And by considering that also, the ARMIA process or model is proposed that considers the fluctuations of the signal due to different noise signal variations and input signal amplitude variations. Due to different fluctuations of the signal that is input to the system, the autoregressive integrated model can take that also into consideration and predict the parameters of the model based on that. So ARMI model is a more enhanced version of ARMA model. So I think that is also something important. So when we discussed about the AR models and ARMA models, we we have to actually finally estimate the values of the parameters that define the ARMA process. As I said before, like this ARMA process that we have in here. Let's go in here. So ARMA model that we have in here is determined by different parameters related to phi I and theta j in here. So these values must be known in order for us to proceed further. So there are like different methods that we can do that. And also like after we have determined the values of this phi I and theta j, we have to use this process and we can, use this, use other methods to, like determine the uh, determine the optimal filter coefficients that will give the same behavior as the input signal. So I think I will explain that using using some derivations, uh, and I will use something called the Yule-Walker method. Yule-Walker method, which we use to estimate parameters of these kind of ARMA processes. So this Yule-Walker method is something that I'm going to discuss, and it can be used to estimate unknown parameters in the ARMA models, and also to predict optimal filter coefficients for ARMA processes. So we will discuss about such kind of a case before going. Before going to the filtering step, I will first explain what Yule-Walker method is. So if you have any questions, you can let me know right now. So we will start with the AR model. AR model, which is defined using this equation, which is like AR model is a combination of different parameters, and it is equal to the like it is equal to the white noise values. So in the previously, I think we have seen the model of AR. So in here, AR model is given. So this AR model, it's a combination of different components of X signal, and it is equal to the WT, or the white noise random, white noise component, random error. So the past and the present values of the time signal can be equal to this white noise component. So I can write that mathematically using this equation, where I use this k equals 0 up to n, and I use this ak to model the like five parameters that I mentioned in the previous equations. Instead of using phi, I'm going to use a parameter in here. So a is the constant that I'm using here. So this is equal to the white noise component. So this is the AR model. In here, we have to also note that A naught is assumed to be 1, which means that the component of the component or the constant that is related with the x n, or at the time n equals 0, the a value is going to be 1. We are going to consider like combination similar to here, where we have the a naught value, like in here a naught value is 1. Therefore the constant in here is most of the time maintain 1, in order to keep the standard pattern of the ARMA processors, and likewise. So we can actually derive the Yule-Walker equations using this model. So first we are going to multiply this equation with this is equation, let's say a or something. I'm going to multiply a with xn minus L and take the expectation. So the same expression has been taken, and I'm going to multiply each of the expressions from this expression xn minus L and take the expectation. So this is by definition the autocorrelation when the time gap between this is L minus K. So we can simplify and write this. However, in order for us to find the simplified version of this expression, we need to consider the product between the white noise Wn and Xn minus L. So for that, we can consider Xn minus L separately. So we have to note that Xn minus L is equal to this, like by substituting in here, right? By substituting in this first equation, where the K value can be made to L, we can write that the So if we take the first term as xn minus L, then we can, it's like you're substituting n in here with n minus L, right? So you have to substitute in A. Right, n equals n minus L in A. Once you do that, you can get an equation like this. So this is exactly what we are looking for in here. So this is exactly this one. So we can substitute this expression inside here. We can put this inside in here, and then we can calculate the expectation. So we can consider two cases as well, L equals 0 and L not equal to 0. So first we consider L equals 0 and we try to substitute this term into here. Right, so we make the L equals 0 in B. So the result we got in here, we are going to substitute in the equation C. So substitute in C, and in there specifically we are going to consider this part because we want to simplify that further before substituting to, considering the rest of the equation of C. We are going to first consider this part, and so by substituting this part in there, right? So we are going to substitute this section into here because in this case we are going to consider for the case L equals 0. So in that case, the this is the white noise, right? So this is a white noise. So what you, as you know, white noise is a very random signal, and that randomness cannot be compared with another signal. So if we take X signal, xt or xn, right? Xn, it is completely independent with the wn. No, xn and wn are independent. And therefore, once we take the expectation between these two components, the product of these two components, we are taking the expectation of the product between these two components in here. Once we take that, it will be 0. Expectation will be 0. And then once we take the expectation between the products of wn and wn, of course that has a value because we are taking the random value of wn exactly with the wn. That means that although wn is very random, its autocorrelation value is going to have a value at n equals 0, or then there's no time gap between those two signal components. Right? There's a value for the autocorrelation when when the time gap between those two components or those two values is 0. So at tau equals 0, there's an autocorrelation value in here. So that value is something that is there, and therefore it is not 0. So we have to, if we know the value of the way that random noise can be, modeled by certain, uh, like modeled in a mathematical manner. So it will have a certain variance, and it is given by sigma squared W. So this expression gives the variance of the noise, and it is equal to the sigma squared W. So this expression therefore will equal to sigma squared W when the L is equal to 0. So however, if L is not equal to 0, then what happens is that there's a value for the L in here. So if we consider that situation, right, we take the expectation of these two components when L is not equal to 0, then in here, there's going to be some kind of L component in here. And in W also, there's going to be some L component. So So if we take the expectation between the product of these two, again, it's going to be 0. And once we take the product between these two components, Wn and Wn minus L, again, those products will result, the expectation will result 0. The reason being Wn and Wn minus L points are again completely independent with each other. There's no relationship between these Wn and Wn minus L points because they are too random. There's no similarity between those two components, and that is why it is known as a white noise and random noise. That is why it is known as random noise. So the noise value is too random that the one component at one time instance cannot be made equal to any component in the other time instances of white noise. So in that case, of course, now this value is going to be 0, Wn xn minus L. So therefore, as a summary, like regarding the value that we can input in here, right? We are trying to find a relationship between this autocorrelation function and the input and this, this expectation value. So the value of this expectation will have a value only if the L is 0. If it is not 0, then it will not have a value. So by considering that, we can write uh, that conditions for this autocorrelation variable. So in summary, we can write that this so there's a value for variance only. The value for this expression will have a value only if L equals 0. If it is not 0 or above 0, then it will have a value of 0. In all these conditions, we consider that A naught value is 1. So, so by this expression, we can form the Yule-Walker equations. right? So Yule-Walker equations can be formed using this relationship. So for cases where L is not equal to 0, where L value is not equal to 0, we can consider right. L is like a gap, time gap. So we are going to consider that value is something either positive or 0. And if it is positive, then the expression will be we can also consider that in some other method we can actually put the first term into one side. So I can write k equals 1 here and then put rxx L minus k equal to minus rxx L. So this is the like expression that we can derive from this. We have taken the k equals 1, k equals 0 term out, and we have put it onto the right hand side. So this is one equation that we can consider as Yule-Walker equations, one relationship. Another relationship can be taken by considering the for L equals 0 condition, where the values of all the sum of all the values of this equation equal to 0. Sorry, equal to this variance value, which is sigma square W. So this is the second equation that we can have for the Yule-Walker equations. So these things can be used to find the values of, like this value of this correlation matrix Rxx. This one we can find by solving these A and B equations. If it is not known, if we don't know the properties of Rxx or the autocorrelation matrix of the input signal, if we don't have any idea about the input signal, we can use these two equations and find the value of Rxx, assuming that we know the values of AK values, so A constants values of A. Assuming we know those values, we can find the values of the Rxx or values of the autocorrelation matrix of A and proceed. So this equation is an equation which is used for uh, the calculations of the like unknown Rxx matrix and also such related unknown parameter estimation. So this is a very important equation, and therefore it is having a certain name as well. So a lot of people call, different, some different names are there. So another one name is order recursive algorithm or order recursive update. So order recursive update algorithm, or this equation is known as order recursive update equation, or else it is also known as Durbin's algorithm. So, this a the question the equation A is known as also Durbin's algorithm. So the like this equation A can be also, can be further expanded into a matrix representation. We can represent by considering L equals 0, right? L equals 0, we can consider this equation. For L equals 0 in A, we can write sorry, L equals 1. L equals 1, we are considering the A equation. For L equals 1, so when A equals 1, the equation, if you see, the K values change from 1 to N. So the first instance of this expression is that L minus 1. So L minus 1. So L minus 1 means like if L is 1, then Rxx 0 should be. So it's Rxx 0 in here. Second term will be Rxx. In there actually, it is L is 1, then 1 minus 2 because K value is 2. So that means Rxx minus 1. Up likewise, we can write up to Rxx, 1 minus N. So in here, we have to get the same expression as well as A. So we have to multiply this Rxx with A1 coefficient first, Rxx minus 1 with A2. Likewise, up to An, we have to keep the coefficients in this vector, in here. So up to An, we have to multiply. This is equal to Rxx 1, right? It's going to be 1 Rxx 1. So similarly, this is going to be Rxx 2. Likewise, to Rxx n points are going to be here. So apart from that, like once we consider the input matrix, we can write the elements similar. So this is one vector. So just hope you can understand this is a vector in here, column vector. Considering L equals 2, we can write Rxx minus 1, Rxx minus 2 likewise. If it is L equals 2, that means it's 1 actually in here, Rxx 1. In here, it's going to be 2 minus 2, right? 2 minus 2 is 0.